recording, so we can start now. And today we'll pick off from last Thursday, and we'll now talk about some other things that make CPU slow, right? Because at the end of the day, when you run a program, what impact the performance is how fast can you execute that lines of assembly inside the program, right? So at the end of the day, is what matters. I give you assembly code, how fast can I finish it? And how fast can I finish it kind of like dictates the whole performance in the CPU. I take in the instruction, how many nanoseconds, how many milliseconds do I need to take to process that instruction? So we talked a little bit about pipelining, right? This is a quick recap. Sorry, I think the my computer lags. I'm supposed to show this recap followed by this pipeline and processor design, right? So we mentioned this super classic 5-stage pipeline. The word 5-stage pipeline is something that you see from the traditional architecture textbook for undergrad. So if you buy any textbook for aiming for undergraduate students that want to study computer architecture, this is the core design. The 5-stage consists of fetch, decode, execute, memory, and write back. And the name follow what they're supposed to do. Fetch is I'll go and get the instruction. Decode is now I have the instruction. I'll figure out what are they supposed to do. Execute means that I'm gonna execute that line, actually doing the action. Memory is if I need to access the memory, I will handle that during the stage. And then write back is when I finish the instruction, I need to save the result so that I can move on to the next instruction. Sounds simple, right? And this pipelining allow you to kind of like fully use all these wires, components, adder, decoder, the program counter, the memory all at once so that you have a better utilization. Remember our like washing and drying clothes example, right? That's a great way to motivate why do we need pipelining. We have one washing machine and one drying machine. We want to make sure that they are running at the same time all hours so that I would minimize the amount of time that I have to take to finish dealing with my daily laundry that I haven't done. But what are the key issues? So each stage, right, is handling different instruction, right? So it means that the design somehow need to process 5 instruction where the fetch is dealing with instruction number n. Decode is one line above that, right? N minus 1. Execute is instruction n minus 2, 2 lines above that, so on and so forth, right? And now the programmer will only see that instruction n minus 4 is about to be done. And when that write back happens, that's when the programmer see the changes, right? So because we have this concept of ISA and microarchitecture, this should be done in the microarchitecture such that programmer don't have to worry about this. As a programmer, you don't even have to think about, okay, what's going on, how many pipeline stages are there in my CPU. You just program and it magically works, right? While you might think your C program is super complicated, there's so many steps that are going on underneath so that your program can run in 1 second rather than 10 seconds, in 1 minute rather than 1 hour. So these are what the CPU are designed to do without telling the programmer. We basically make things faster. And the register file and the program counter is going to be updated to the programmer, right? At writeback. Other state has to store its immediate value. So a quick recap, to do this, we would add the pipeline register, which it basically store these intermediate states. One for fetch, one for decode, one for execute, one for memory, to make sure I can remember as a temporary variable tied to that instruction inside the stage. And this can be quite costly, but it's worthwhile. So every single chip you buy nowadays would have this done, right? But still with pipelining, we talk about what can happen, which is instruction stop, right? there's not enough resource to move an instruction through the pipeline. So the effect is my program gets slower. What can be the case? Not enough ALUs. You can't go and access certain things under the really, really quick amount of time. Think memory, right? Sometimes your design is just simply unbalanced. Things like instruction stall, like if you want to actually make sure they're faster, you need to still make sure you still produce correct results. What do I mean by that? We kind of end the lecture on Thursday with data hazard, right? So from this example to back from Thursday, we look at this particular program where the first multiply generate the value as 0, which used in the next instruction. With pipelining, we can't tell the value as 0 until write back. So we have this problem of data dependency, right? And it's a really, really common thing in your typical program. And if you look at it, there are 3 types of data hazard. And in this class, in this semester, you see the first type only, because we are dealing with in-order pipeline. So what we see in so far is called in-order 5-stage pipeline. Only the first type exists. You are not gonna fix it. Again, sorry about this. Copy and paste error. I should not have done that. Sorry, guys. No need to do that. Assignment 2 is already over. So in order pipeline, only raw hazard exists. So you take the full-blown special topic class, you have assignments where you implement a simulator for a real processor that run a real program. And then you do this data forwarding, which is what we're gonna talk about next. So the concept of data forwarding is simple, right? You want to move the instruction forward in the pipeline, but there's data dependency. But because your data R0, for example, from the multiply is available right away, is on those wires. So you can forward, right? You don't have to wait until write back. You can forward the results inside the pipeline to the future instruction right away. So for each instruction, you will check the source. You check who generate that value. Is there data hazard? If there's data hazard, do I have the data? If I have the data from the ALU already, hey, let me steal that data for myself so I can process the instruction right away. So this will solve the raw dependency, read after write. And the benefit is your program would get actually a lot faster. Right? So that's a quick recap of the lecture on Thursday. Now we'll go through the next big thing that the CPU these days magically fixed for you. Branches. So what are branches? Can you give me some example of the C code that introduce branches? Anything you remember? Anything remember that generate a branch in your code? Anyone use if else or for loop in your program? Anyone? So are those a branch? Are there 2 possible directions I can go from the next line for basically when I want to compute the next line of my code for both if else and for loop? So for if else, what are the 2 directions I can go? The if and the else, right? How about for loop? I'll let you answer this one. How about for loop? What are the 2 possible directions I can go? Yeah, you loop or you exit the loop, right? So if else, if you have a code block that run into the if else, you can either branch to the if or branch to the else. Loop is something like this. Loop condition. You repeat the loop or you exit the loop. So if you have this code block that are in the loop, you can have the 2 choices, right? And if you study things like advanced compiler, you understand why do I draw these blocks, but let's keep it at that for now. Basically, your code can go into multiple directions, and that's branches. So these are called control dependence. The classic example is if else and for loop. What else? How about switch case? Switch case. Are these also code branch? Or to move things forward, the answer is yes. Switch case is also a code branch. You have to jump somewhere, right? So how do we handle the branch? How do we handle the branch, right? And we will also talk about, are there any better options than just stalling, right? So let me tell you this. Whenever you see this word stall, what does that typically mean for performance? When you look at the performance of a CPU, if I see the word stalling, would that increase or decrease performance? Just look at the word. Yeah, it's gonna slow things down, right? So that's bad. Basically, you as an owner who buy this really costly CPU, which I mean everything out nowadays is so costly, inflation, yeah. Did you know we just have like a record-breaking like inflation rate in Thailand that we never had for a while? So I think it's gonna get bad. Anyway, so stalling is bad. You buy a CPU, you want them to be fast, and somehow the code you're writing has a pattern that can slow down your CPU. How does the CPU, the hardware as its own, handle this, right? There's a are you talking about the bubble in the pipeline or a real like inflation? Yes, I think there's an inflation going on. I think it's super sidetracked. Sorry. I mean, look at how things cost these days compared to like 5 years ago. Everything is so expensive. I'm not sure if you would call that bubble yet, but yeah, in my opinion, yes, everything these days costs a lot more. I don't know. I have no idea about that. I would have been. I guess I'd be rich if I can predict that. um, I mean that one is hard to tell, right? Anyway, so and because I'm not expert in that area at all, for sure, right? I'm doing computer science and engineering. Yeah, hopefully we don't have the flashback of 2008. That's crazy, for sure. But I mean, if you look at stock market, like Nasdaq has been down since the war started, so we'll see. Um, anyway, so if you want to handle, so let's go back to the bubble we talk about inside the pipeline, right, guys? I mean, let's let's first focus on the class material, right? So how can we handle that? The first option, you already said that in the question. Send the bubble in. You stall the pipeline. Basically, you send in the bubble throughout the pipeline, saying, "Hey, I don't know what to do with this branch, so I will not doing anything until I know exactly, am I going to the if or am I going to the else part? What else can I do? Anyone have a true or false questions and you don't know the answer? What would you do? Exactly, right? So classic computer, one thing you can do, if you don't know, if you have no clue about the question, you would go with this solution. I'm gonna blindly guess, right? Obviously. But if you know a little bit about the question, what do? You would go to the educated guess route, right? So this educated guess is what is available on the CPU. And the beauty of that is we are actually getting close to actually more than 95% correctly. Is it nice? Think about it, right? If all your exam is about true or false, then the CPU somehow can make the decision that would get 90% of the choice correctly. If that's an exam, you would have gotten an A just by educated guess, right? And how? So let me ask you this. If I'll talk about this educated guess option for a bit, right? Because that's kind of like the main design in the CPU. So if you want to study and you want to take the true or false exam, right? How can you put yourself in the position that you get close to 100% chance of getting the question right? So what would you do? What's your typical strategy to do that exam? What are you supposed to do? Exactly. One thing you can do is you go look at the previous test and you do the practice exam, right? What else? What else besides practicing over the previous version of the test? What else can you do? Anyone study for exam? Yeah. Well, thank you for letting me know that I should check your P3 and your quiz quite a bit. Yes. Copy from a friend's, not exactly legal, but I mean, if I train my brand's prediction logic, I then can copy the same logic for the other CPU I design, right? You can also study for the test, right? Look at the history of how the program behave, for example, can tell me likely the direction of the branch, right? Let me give you one example. If I'm in a loop, if I am inside a loop in your program, what's the likelihood of me? What's the more likely chance that I stay in the loop or I exit the loop? If I have to guess, or if you have to guess, what would be the most likely? Repeat the loop or exit the loop? Yeah, exactly, right? The answer is it's much higher chance if I stay inside the loop. The reason behind that is how many people write the loop that only loop twice and then exit? Not a lot, right? My loop would have like 10 iterations, 100 iterations. So if I guess that I'm gonna stay in the loop, I'm gonna be 90 to 99% correct already, right? So that's an educated guess. You can predict from the pattern that you see. You can do, so this is something that we will not cover today. We'll cover that in the next class if you're interested in taking, but we'll talk about things like a technique called delay branching. Basically, well, I'm not doing anything, I'll find something else to do for that one instruction that I'm sending the bubble. I can do something else. This is the option the GPU is taking somewhat, right? I would do fine-grained multi-threading. I can get rid of the control flow, right? So GPU would do the two options together. So you would kind of like do the combination of predicated execution and fine-grained multi-threading. Again, we're not going to talk about this is in detail in this class. I want to kind of motivate you that, hey, real hardware that you buy these days, use these tricks that we learn in this class. You can do multi-part execution. I have a lot of hardware resource, so I'm gonna run both sides of the program until I know the result, and then I'll drop one. I'll drop one part, and it's like, okay, I don't need that. So naive solution one, stalling the pipeline. Basically, when do you know that you are running to the branch instruction? When are you gonna know that you have to check if you're gonna fetch PC plus 4 or something else? Is that in the fetch or so actually it's in the decode, right? Decode would tell you the opcode, so that's when you can tell if this is a jump or a branch, like branch if not equal to 0, right? You know that in the decode. When will you know the direction of your branch? When will you know, are you taking the branch or not? When do you know if you're taking the branch or not? Execute, right? So if it's branch, if not equal 0, execute unit would be like, I'm going to compare this to 0 and see if it's equal to 0 or not equal to 0. So this would give you the direction of your branch. And when do you know where do you branch to? So let's say you have to take the branch. There are two possible places that you know where you branch to. If you branch to the address pointed to by the register, then you know it right away from the execute because you already have that in the register file. If you branch to a place in the memory, then you also know the address of the branch, right? You know the address of the branch from the register file as well. So from here, you know it's a branch. From here, you know the direction. So if I have to stall, when my branch is here, what do I put in here? Now I know I'm in the decode. I know it's a branch. What do I fetch? What do I fetch? Let me ask you this. Now, can I fetch the next instruction? Or I cannot fetch the next instruction because I don't know if I'm going to the if part or if I'm going to the else part. I have to wait, right? Basically, I have to wait. I will have to wait until I figure out if I'm doing the if or if I'm doing the else in your code. So you have to stall. And you have to wait until this is here, right? Now you know the direction so you can fetch. So let me move on to this. How many cycles does it take for me now that I have the branch instruction in the middle? Now that I have the branch instruction in the middle. So first I'll do fetch decode. The first instruction has no problem. I can fetch decode, execute memory, and write back. Yay, life is good. I fetch in cycle 2 for instruction number 2. In cycle 3, I decode. Now I know it's a branch. So I can't fetch. I cannot fetch instruction 3, right? I know it's a branch, so I have to wait until the result, which is in the execute. And now I can fetch because I now know what's my next instruction. All right. So this seems like, well, things are slowing down, right? Things are slowing down. Is my performance reduced? So how much performance reduction do I have here? From 8 cycles, I would take 9 cycles. So it's not a lot, right? It's not a lot. But in modern processor, imagine the fetch and decode would take multiple stages. It gets bigger and bigger. So the cost gets much bigger in the real world. So this problem is actually pretty big. All right. But it's not as big in a 5-stage pipeline. Anyone with anyone have a problem or questions? Are you guys with me so far? Anything confusing yet? Yeah, branch not equal. B and E is branch is not equal. So we'll check R0 and R1. If they're not, right, if they're not the same, you branch to the address pointed to by this value immediate. So immediate can be address 0x20. It means that if R0 is not equal to R1, then you go to address 20. So that's your next instruction. If they are equal, you go to the next line, which is XOR R6, R7, R8. Is it more clear now? Yeah, basically you need to now figure out, are you fetching the XOR instruction number 3, or am I fetching a totally different instruction? And the problem with this is for instruction 2, right? For instruction 2 right here, I cannot tell, even with data forwarding, right? So this is already assuming data forwarding. So even with data forwarding, I have no idea if R0 is going to equal to R1 or not until I am on this execute stage, right? So that's when I can fetch, right? So that's when I know it's safe to fetch, right? So is it more clear now? All right, perfect. Yeah, basically, if I'm not blindly guessing, I have to wait. I have to wait until it's extremely safe for me. Okay, that's the next instruction, right? Now let's blindly guess. So for blindly guess option, I'll skip this because it is the same thing. I'll go back to the same code here, right? The same code here. So if I'm guessing that I'm gonna fetch the next instruction, if I have a branch, in this case, what would happen? So let's assume it's a correct prediction, because when you're guessing, there are two things that can happen. You're either correct or you're wrong, right? You're either correct or wrong. So let's assume you're correct. You fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, write back. Right? And now I'm on the instruction 2. When can I fetch instruction 3? Now that I'm just guessing that I'm gonna go run instruction in the next line. So when should I be what cycle here can I fetch instruction number 3? Now I'm assuming we are guessing that, hey, it's gotta be instruction number 3. So yeah, so cycle number 3, right? At this cycle, right? When you decode, well, I don't care. I'm gonna guess anyway. So sorry about this text disappearing, just PowerPoint fighting with me. So I can fetch, decode, execute, memory, and write back as usual, right? So now we finished one cycle earlier. If we predict correctly, everyone with me so far? Because we are guessing that we're gonna fetch instruction number 3, I'm gonna fetch it anyway. Now, how many people here wondering, so what if I guess wrong? What? I'm not sure if there's yeah, yes, yes, exactly, right? You redo. If I predict incorrectly, so let me ask you this first. If I do an incorrect guess, does the programmer see that? Does the programmer see that, hey, I'm guessing incorrectly? Yes or no? So when will the programmer see instruction 1 finish? What cycle in this example? When will the programmer see that I'm done with instruction number 1? Yes, exactly. At the end, right? At the end of instruction 5, this is where the programmer see instruction 1 finish. I will see instruction 2 finish right here. Instruction 2 will finish right at the end of cycle number 6, right? So do I see any effects? So when can I tell? When can I tell that I'm going into the wrong direction? What cycle? When can I tell that branch not equal, that R0 and R1 is actually equal? Oh, actually not equal, my bad. Basically, you're branching. What cycle do you know that? Right? At cycle number 4, you know the result of the branch. So as you said, right? If I if I just hide my incorrect prediction and I restart instruction 3, will the programmer notice? Will the programmer notice anything? Oh yes, exactly. The only thing they'll notice is it's got a little bit slower, right? It got a little bit slower, but that's it. It's not like you're gonna produce incorrect results because you haven't even write it back yet, right? So here's what happened if I have the wrong prediction, right? If I have the wrong prediction, I'll do this. Fetch, decode, execute, memory, write back, fetch, decode, execute, memory, write back, right? And then I try to fetch, decode, and oops, at cycle number 4, right? At cycle number 4, I know it's wrong, so I need to get rid of that. We call this flush, right? What does flush mean, the word flush? What does flushing mean? Yeah, basically throw it away, right? Clean it. So now what you do is to flush the pipeline, clean that, right? Make it look like nothing happened. Yeah. So now you're knowing it here. So you can fetch here the code with the correct one, right? Now you know, so you flush. And that's it. Now you know where you're branching to. So you just need to flush and clean it up with the correct path, right? So anyone have any questions or anything unclear now with the how this is actually happening on your CPU? Oh yeah. So great question. Great question. Over here, right? You know that you're wrong during the execute, right? Because the execute is the point that you know what direction of the branch you're going to. Okay. Sorry. Let's begin again, right? Everyone okay with instruction 1, right? Nothing to do with branching. With me so far. Instruction 1 is okay, has nothing to do with branching. Instruction 2 is branching, right? But the problem with instruction 2 is I'm guessing. I'm guessing that I'm going to go and run XOR R6, R7, and R8. The issue here is my guess is wrong, right? So my guess would put me at this situation. I'm going to fetch, right? I'm going to fetch here because I'm guessing, right? And then I'm going to try to decode it here. Instruction number 2, the branch not equal by cycle number 4 is basically comparing R0 and R1. So when I finish comparing R0 and R1, what can I tell? What can I tell after I finish comparing R0 and R1? I will know, right? I will know exactly where do I branch to, right? Whether I'm gonna do this XOR or I'm doing something totally different. Right? Are you with me so far? All right, awesome. So because now you know, if you guess correctly, do you have to do anything? If you guess correctly, you're fine, right? You just keep fetching, decoding, and everything is perfect. But in this case, I basically said that, hey, I assume that I guess it wrong. So because I guess it wrong, I need to get rid of this, right? Because it's this XOR, and I'm not supposed to do that XOR. It's wrong. So I need to clean it up. And now that I know exactly by cycle number 4, I know exactly what instruction am I fetching. I can start the process of fetching, right? So I can start the fetch stage at cycle number 4 for the correct instruction. Right? With me so far? All right. So that's why, right? That's why things will slow down a little bit in the 5-stage pipeline, right? And you might have think that, hey, it's actually not as bad as a pipelining. I guess the benefit of pipelining over multi-cycle architecture where you have to do like 5 cycles for an add and can't do anything else, right? But imagine this. Imagine modern CPU where fetch has like 7 to 8 stages. Decode is another like 6 to 7 stages. Now, when will I know the outcome of my branch? When will I know the outcome of my branch? If you look at the modern CPU. So this is a little bit too aggressive. So let's say fetch is like 4 to 5 stages. It's actually not that bad, right? Okay. So let me answer that question first. Why is instruction at cycle 4? So it's not instruction 4. It's cycle number 4. At cycle number 4, instruction 2 is in the execute. Because instruction 2 is in the execute stage, it is doing this R0 equals R1 or not. And now it has the answer. Because now it has the answer, it knows exactly where to branch. So now it knows, hey, I'm wrong. All right, is it more clear? Cycle number 4 for instruction 2. Okay, awesome. But yeah, so now with modern processor, you have to be around the execute stage, right? But you're not in the execute stage after like 12 or 13 cycle. So what it means is when you flush, you're flushing a lot of instruction that you have been fetching. So this can be bad for performance if you are doing it wrong a lot of time, right? So now the goal, right? The goal of a good branch predictor is to guess correctly a lot, right? So what is the simplest form of guessing? Let's say I have a true or false question and I need to have you come up with a strategy. What's the simplest strategy you can do for guessing, I guess? Let's say you can't call a random function. Let's say you cannot call a random function. What's even simpler than calling a random function? Anyone here like been in those like exam where like I have no idea about the exam at all. I just gonna go straight through, like pick one choice. That's it. It's a simple way of guessing. So there are two separate questions. Is that a simple way of guessing, and is that a good idea for guessing? It's simple, right? You don't even have to think. You always pick one choice and that's it. And if it's uniformly distributed, you're likely to be correct for 50% of them, right? 50% chance of getting it correctly. If I'm in a code with lots and lots and lots of blue, if I'm in a code with lots of blue, what should be the simplest form of guessing? I should be guessing that I'll stay in a loop, right? Then I'll have probably a high chance of getting things correct. So the always predict certain thing can work relatively okay. For example, right? For example, you can always predict not taken, predict taken, right? You take the branch or you're not taking the branch. This can work well in, for example, in a loop, right? In a loop. Can you do something else to help? Yes. That's actually, I'm not sure if I should bring it up or not, but there's a paper in 1990s, for example, that look at the program and give the hint so that I'm going to modify the program assembly that if I know that my hardware is basically guessing true, or false, I would then modify the program to increase my chance of getting things correctly. Anyone here can think of a downside of this strategy? Is this a good idea? So let's say you have to take an exam, and I tell you, let's just pick one choice and that's it. What should you tell me back as a student? So as a teacher, I tell you, okay, go in and pick one choice and that's it. What should you tell me? Yeah, like that's a dumb decision, right? No, I'm not gonna do that. Why would I just guess only one choice? It's likely to be ineffective, right? And I will fail the class. Uh, the thing is, again, you need to think about the cost of branch misprediction, right? So for the 5-stage pipeline, without anything aggressive, basically you would send 2 bubbles, right? You are eliminating the fetch and decode that you have done already for the earlier instruction, because by the time you hit execute, you already decode one and fetch another one. So 2 of them are now wasted. Yay, right? So let's say you basically are having this overhead of 2 bubbles. And let's assume that your program, 10% of them are either in a loop doing this true or false or if else. So 10% of your assembly is control flow. And 80% of them are taken. What's the performance of your program, assuming I always guess not taken? Assume that I always do not taken. How many cycles I can finish per how many cycles does it take for me to finish one instruction? So let's assume I have 1,000 instruction, right? 1,000 instruction. With 10% control flow, how many of them are branch? What's the 10% of 1,000? 100, right? And 80% of branch are taken. So in this case, how many times do I predict wrong? How many times am I wrong with this prediction? I have 100 branches, 80% are taken, 20% are not taken. So in this case, I am going to be wrong 80% of the time, right? So 80 times is wrong. Each one of the wrong choice, I spend 2 extra cycles. So in total, right, I have 920 instruction that I do it correctly, right? Each one of them would take 1 cycle to finish on average. And then these wrong choices, I would spend 160 cycle extra. Right? So in total, you spend 1,080 cycle. instead of 1,000 cycle. Right? Because if you guess everything correctly, 1,000 instruction, I expect them to finish with 1,000 cycle. Now you're spending 80 cycles more. Now you're basically spending 80 cycles more, right? What's the percentage slowdown? How much slower is your computer? 8%, right? It's actually quite significant, right? I can tell you that each generation of the Intel processor, like every single year, they're not going to be 8% faster, right? Always 8%. That's a big jump. That's a big jump in a year. So having your processor 8% slower is quite a lot, right? On average. So roughly, yes, probably not too much of the lifespan, but it consumes more power. So basically, it drains more power to compute those useless instructions. Because you have to fetch and decode those, and you have to throw it away, right? Exactly, basically, waste power. But in this case, if you do a good job at guessing, right? Over here you have again 1,000. Let me use a different color to make it clear that it's a two different example. Let me do rate. So over here is 1,000 instruction again. 100 of them is a branch, and only 10 of them are wrong. So instead of 1,000 cycle, you are spending 1,010, right? 1,010 cycles. Because you are 90% correct here. Only 1% slower. So it's not too bad, right? Not too bad. Only 1% slower. So what would be the typical goal of a branch predictor design? I want to, sorry about this, I write over my own text, but the text said I want to make sure the branch is more accurate. I want to make sure I can predict the branch well, right? And that's all. To do that prediction, right? To do that prediction, this is a little bit beyond the scope of what I want to teach for the class, but I want to prime you for in case you want to do the next class. You want to figure out first thing first, is that instruction a branch or not? Is that a branch or is that an add or subtract? So that's the first thing you need to figure it out. The second thing is you need to figure out what direction am I going? Is it taken or is it not taken? And then if it's taking the branch, where do I jump to? Do I jump to address 10? Do I jump to address 1000? So these are the three things that that we'll learn in the next class where I can offer that class if there's enough interest. And we'll also discuss another option to handle things like what if the GPU have to branch, right? It actually assume a different way to compute your program. So it would use the technique called fine-grained multi-threading and predicated execution to run the program and to make sure it handles branching. Another example, how many people use Android phone? Right. So there's a version of one of the brand. I'm sure many other brand might have used it as well. These idea actually spawned from a paper in HPCA 2001. HPCA is one of the top venue for computer architecture. So if you work in computer architecture, there are basically four places that you would dream of submitting and getting the paper accepted. ISCA, Micro, HPCA, and ASPLOS. So this paper is published in HPCA 2001. It's called Dynamic Branch Prediction with Perceptron. If you are taking class like AI and machine learning, you might have noticed the word perceptron. Basically, this is one of the like basic method to do to train and to do kind of machine learning, but it is simple. It's simple enough that you can implement this in the hardware. So basically, the key idea is I would try to correlate all your if else and for loop using perceptron, and then I'll assign the weight of that correlation, and then I'll use technique called supervised learning to perform branch prediction. And from that paper, the author actually now got the award called Test of Time Award, which is awarded to papers that has real industry impact after multiple years from the paper when it gets published. So the concept actually used in real mobile device nowadays, right? Because it's simple to implement and it's really effective. It's really doing a pretty good job at predicting the branch of your program. And this is one of the example of how how the ideas in research in the design like go full circle and become like an actual product. So we will leave branch prediction at that and now move on to the next topic. I'll give you an option. Should we pause and do a quick break, or should we go on and do a pause right before we cover the project number 3? So want to break now, or let's go on? Okay. Yes, no. Break, no break. Yeah. So let's do a break now. We'll meet again at 3:20. I'll pause the recording so that if you watch the video, you don't have to wait for the break. Sure. Sure. Okay. And now that we talk about branching, the other really, really important elephant in the room that we assume that it's been using one cycle so far, and it's definitely not true, is the memory, right? The thing about memory is it's actually really slow, right? So memory is slow because even with new technology, right? There's a limit on how fast you can move electrons, and you have to actually move the electrons through quite a distance from DRAM, right? From the DRAM capacitor, those black chips that you see on the DRAM DIMM that you buy, right? That you plug on the motherboard, move those all the way to the CPU. It does take some time. Um, Most of the fast programs that use different API libraries and tools are designed to hide, right? This basically the slow memory access. So if you are working in an area in computer science where you would write different tools for other computer scientists or software programmer or developers to use, one of the things that you can do with the tools or the libraries or the APIs is to figuring out how to make the performance better by hiding this slow memory access. And the size of the data also make the optimization hard because I mean I think big data is always a keyword, right? So when your data is amount of data is big, right? Uh, you need to figure out how are you going to make sure that your data access is really fast. So a classic way to speed up memory access is what we learned in system skill, right? We know that there's a fast memory that we can buy called SRAM. Uh, we use it as a cache. So we can be greedy, right? We can have multiple level of memory, right? SRAM is fast, DRAM is slow. So we can have a hierarchy of SRAM before we have to go to DRAM, right? So that the first level of SRAM, which is where your block size in a matrix multiplication should be, the block size should stay in this L1 SRAM cache, right? It would take only less than 1 nanosecond to access. You can have a really fast L1 SRAM cache. And then the few layer afterward would take 1 or 2 or a few nanoseconds to access, right? Still fast, but not as fast. And then if the worst case scenario happen, right? Then you can go to DRAM. That can take between tens of nanosecond to hundreds of nanosecond in the worst case, right? So that's about how slow DRAM can be. 50 to something like 200 or 300 cycles are a typical amount of time it takes to go to DRAM. And the concept of memory hierarchy, if you want to visualize it, is basically something like this, right? You have each layer where you have a cache. They can be a private for each CPU core that you buy. Basically, your CPU come with multiple core. Each core can have its own L1 cache. And then they can have a much bigger share L2 cache, which is then back with a bigger, much bigger memory. And for those of you who've been actually, that's a great question on Discord that I got. Sorry about the reply, which was a little bit late. But like, how about the using the storage as a memory? So those are basically the swap space, which is basically what if your memory is not enough, right? Then in that case, you can use part of your hard drive or SSD as the memory as well. And then it's gonna be really slow. All right. Let's do a quick recap on caching, right? So a basic caching recap is this. Anyone remember this? You have the address. You have the bits that would tell you the byte in block. And you have the index bits. And you have the tag bits. What do we use the index bit for? Anyone still remember from previous semester in system skill? What do we use the index bit for? And what do we use the tag bit for? Almost actually. To tell which block you use a combination of this tag and index. But the index bit give you the set that you want. The tag bit tells you which block in the set. And the byte in block bit would tell you which byte in the block. All right, if you still don't remember this, definitely highly recommend go watch the system skill lecture, because it's a great like 1.5 hour in total of a recap of how caching works. Make sure you have that, right? Make sure you have that in mind, because it might pop up on the exam again, who knows. The index bit tell you that what set you are going to. The tag bit tell you, do you have the data in the cache or not? The byte in block bit basically tell what byte am I accessing. Direct, and then there's multiple type of cache. Direct map cache is I only have one block per set. So if I go map to that particular set, if a tag match is a cache hit. If the tag doesn't match, I don't have to search anymore, because there's only one block. If it's not there, it's not there. I go to the next level. I can go to the L2 or I can go to DRAM. If it's a hit, I return the data and thus access is going to be fast. Otherwise, I search the next level of the cache. And in system skill, we ask this question. Can I have data access in a way that we got 0% hit rate? We got 0% hit rate. The answer is yes. Basically, I can have two access, right? Two accesses. Sorry. I can't write, I can't spell words now. Two accesses, right? A and then B and then A and then B, but make sure that all of this go to the same set. Go to whatever set, just go to the same set. The next access would kick out the old one. So in that way, you have 0% cache hit rate. So that's the downside of the direct map cache. The upside is simple, it's fast. Downside is you can run into this scenario where you never hit in the cache. The way to fix it is you can add the associativity to the set. Basically, what it means is you can have multiple blocks in a set. So basically, this is what it means. I have multiple cache blocks in a set, right? One cache block is one single unit. One set will now contain multiple blocks. We call this set associative cache, where say a four-way set associative cache means I have 4 blocks per set. 5-way set associative cache means I have 5 blocks per set. N-way associative cache means that I have n blocks per set. Downside is if the number n is high, then you need to somehow implement basically a search to go through all the ways to see, is my tag match? Does my tag match? Does my tag match? To check if your data is there or not. And then you can use this concept to go full-blown, fully associative cache, which means there's only one set, and number of ways is number of cache blocks in your cache, right? A cache block can be placed anywhere. And in this case, you need to do a lot of search inside the tag store. This technique of fully associative cache is actually pretty common in software caching. Software caching, because you don't have to make sure I respond in a few nanoseconds. In software, you're talking about millisecond or microsecond, which is a much longer time, right? So what you can do is to use fully associative cache, making sure you manage it in the software, right? So that's about the different type of cache. We also talk about the replacement policy, right? Replacement policy basically talk about this. When the cache is full, you need to find out the block from the match set to evict. Basically, if I have to go to set number 2 and set number 2 is full, what I need to do is I need to kick someone out, so I make room for myself so I can add a new thing in. The policy of who to get kicked out is called the replacement policy. And as we cover in system skills, multiple policy can randomly pick first in, first out. Remember our lab 4 from system skill, that's first in, first out. What we use nowadays is something close to least recently used. And you can also do like least frequently used or some hybrid policy, right? So we kind of focus on, from the system skill lecture, we focus on the policy called least recently used, which is based on the concept of temporal and spatial locality. This is basically how you write your program. Temporal means time. It means that if I use this variable, it's likely that I need to use the same variable again in the future. Spatial locality means if I need to access this address, it's likely that I have to access the address next to it. So in this case, the least recently used would make sure that things that haven't been used in a while would likely to be kicked out, right? The benefit is this is likely to be really effective. But the downside is this. It can be costly when you have like 32-way associativity, because you need to search who is the least recently used one. You have to somehow update the time information and then make sure that you can maintain that in hardware. So this can be a pretty big problem in hardware design. So you read papers, I think from 2000 to 2010, there's actually quite a few papers that get published in scientific community on how to implement something like this, right? And that's even like 10, 15 years ago, right? So these are still quite a bit of a problem to implement. And also even with LIU, you can have the problem called set thrashing, where too many data are mapped to the same set. For example, remember this old example where I have A, B, C, D, and E all mapped to the same set, and I access A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. In this case, LRU is not going to be effective. Even things like a random policy is going to be more effective than this, right? So replacement policy is also another thing that's still important in hardware design. And if any of you have to implement this in software, such as a policy on what data are you going to keep inside the memory, which one are you kicking out to the disk, those are managed by the OS. You have to figure out what's the best policy. If you have to figure out, if I download a file, right, from the internet to your phone, and you have to figure out what file do I keep, what file do I delete and re-download later. That's also like Android is as responsible for that in software. So these things matter. The replacement policy matters for performance, right? So that's one thing. The other thing is now I'm gonna introduce some new stuff that we haven't really covered much from the system skill lecture. The first order thing is handling of write. So we kind of briefly talk about this. When I have a cache block and I update that, the actual data changes, right? So let's say I have L1 and then L2 and then DRAM. And the data over here, the value of address 20. The value here is 20, right? And then I update the address 20 and I change the value to 25. It basically means that now L1 has 25. And what it means is eventually I need to make sure that this value 25 it propagates through the entire hierarchy so that DRAM has the new value, right? Otherwise, the data to the same address would have a different version of the value, the old version and the new correct version. In general, there are two policies. If you read textbook in architecture, typically there are two policies. And again, this is also relevant when you have to do a software managed cache, right? Because when you manage cache in software, you also want to make sure if the user modify the data that get updated everywhere, so that if someone else want to access the data, they have the updated version, not the old version. So the policy can be the write-through policy. Write-through means that if I update something, I update everyone. The write-back policy means that I update the next level only if I have to update it. For example, if I evict something from the L1, that's when I need to know I have to update L2, because that will guarantee I reduce the bandwidth, I reduce the energy required to handle the sprites, and at the end of the day, I spend less time handling this particular update. All right. On the miss, but it's a right miss, you also have a choice whether you can allocate the block or not. So you can basically put the block inside the cache. This is simple, right? This we treat write the same as read. And you can also bypass that totally, because sometimes you have the program that go and write value in an array once and you never touch it again. So if you can detect that, you skip and bypass those writes so you don't trash everything from your cache, right? And when you design the cache, right? When you design the cache, think about it this way. There's many ways to design the policy, right? You can come up with a new replacement policy, a new way to hash things into the index bits so that you kind of balance out all the set, right? There's new way to deal with trashing, or even things like, what if I store compressed data so I can pack more things in my cache, right? So these are all like active topics, both in traditional computer architecture as well as high performance computing, as well as computer system where you have to write your own software and manage cache for different purposes, right? And one last thing I want to talk about is there's not on the exam, but good to know that's the concept of what we call ability optimal. It's actually from one of the old journal paper where the author study the caching policy. Right? Look at how old this is, 1966. So the policy said the ideal, optimal policy for caching is you want to make sure you keep, right? You keep the block in a way that you evict, right? You evict the block that going to be referenced the furthest by the program. Basically, if you can predict the future, you keep everything except for the one that you need the furthest. That's a proof that that's optimal. The thing is, it's impossible to implement, but it's a good way to check if your policy is close to this baseline or not. Basically, it would test the effectiveness of your caching policy. All right. So now the second half of this class, again, is all about recap and things you've learned from system skill. In the next lecture, we'll pick up and now we'll talk more about new topics like memory, as well as like advanced, like I guess things that you might read in articles like how the GPU works and things like that. So we'll now cover in the next remaining two lectures. Before we leave today, I want to do a quick demo for project number 3. So let me switch over to my laptop real quick. Sorry, there's a great question here on the chat. So the effectiveness of the cache would be related to the computer itself. So I guess your question is the performance of the computer would get impacted by how good is the caching policy. Is that your question? Sorry, I want to make sure I understand your question because there's some typo there over there. Uh-huh. And so I guess while I'm waiting for you to finish the sentence, so I oh, performance code with different compare. Exactly, yes. Yes. And that can be pretty big in terms of how fast things would go, right? So if you know how cache is managed and how cache pick things and kick things out and what's the size of your cache, what you can do is to write a program that guarantee that most of the time your array access is in L1. Basically, this is what project 3 is trying to get you to do. Make sure your data access, i.e., that's the array access, go to the L1 cache and hit, and that's it, right? A lot of application can speed up quite a lot if you modify the program to make sure this happens. Why is that the case? Most of the time, your L1 takes about 3 to 4 cycles. L2 would be like 10 cycles. And DRAM, basically, you're looking at 50 to 200 cycle, right? So if you can make sure that your program, every time you need an array, every time you need something in an array, is in L1, you basically only spend 3 to 4 cycles with that, rather than 3 times the amount, which is L2, or 10 times the amount, which is in DRAM, right? So if you do it well enough, a program that never have anything to L1 can speed up by 10x the amount if you can maintain that within the L1 cache. So is it more clear? Is it more clear? And this is actually really important as we go into like a big data application where your data is so big, right? That just unless you think about it, there's no way you're gonna put that into the L1 cache all the time, right? So with big data application, then you have to have a strategy on, but how do I take advantage of that? How do I write a program that at least I get to use the L2 or I get to use the L1, hopefully most of the time, right? In that case, your program will be a lot faster. And as I said, there's quite a lot of modern application, modern real use that you can see things speed up really significantly with just this trick. But not all our algorithm is as easy as your project tree. So matrix multiply is one of the most obvious. So that's why we start from there. Yeah, it take a lot of time to just loading this huge metrics for sure, right? Um, there's actually quite a number of techniques, including things like prefetching. So, uh, before before we move forward with the discussion, let me save the slide for now, making sure I have the slide saved, and then I'll switch to my desktop. All right. So give me a few seconds here. And to be honest, another thing that why the concept of caching matters is we don't just use it in hardware. There's certain times that let's say you have to manage a lot of data in multiple data center. You also need to make sure that the data you about to use is as close to you as possible. Anyone realize that if you go to like Google or Facebook and you search for something that you haven't searched in a long time, it would take a little bit more time to search. So I just disconnect and connect on my laptop. That's why I pause a little bit. But yes, so things like web cache or data center also has its own way to cache the relevant data to the data center that are close to you. For example, um, if there's gonna be a concert of I know like Lady Gaga concert in Thailand, there's likely to be a spike in the search for that concert, right, on the Thai server. So Google would have used that opportunity to move that particular set of data, the news and everything, to the server close to Thailand, like the one in Singapore, so that when you search, it's a lot faster. So that's one example of how the same concept called caching can work to your advantage. All right, so can you see my screen? And I'm sorry, I forgot to open up the chat. So here, and you said, yes, thank you so much. So now that you see the screen, what I want to point out is when you download the project starter, right, when you untar that, you can untar by doing this, tar dash extract and BBL. That's why, right? And then hit enter. I already did that, so I'm not going to do it again. I already extracted in this folder. what you can see, right? What you can see is the first thing is the Python code that the only purpose of this is to generate a random integer. That random is between 0 to 5, so that when you do the matrix multiply, they don't overflow. And you can put in the size, right? The size is the first argument to this particular script. So what you can do is do something like this: Python mmgen.py and 1000, for example. It would spend some time. It would generate the metrics of size 1000 by 1000. It does take some time. Into 3 files. So this is the first input matrix, as you can see, is 1000 by 1000. And the second input matrix, as well as the reference, which is the result. So at the end of the day, you want to make sure you compare your output with this and make sure that it's correct. And the task is this: if you go to mm.c, so that's where most of your code has to be done. Task, I already break it down by different tasks. The comments are in there. So task 1 is actually pretty simple. It sounds complicated and kind of weird. Basically, what I want to do is to measure the performance of your code. One thing I want to measure is none of the data is kind of preloaded into the cache by accident, right? I want to make sure that now the cache is empty. So you can write the code to flush your cache. So to flush the cache, right? There's a system call in Linux. For example, if you go and look up on Chrome, there's a system call called cache flush that you can use, where you put in the starting address, number of bytes you want to get rid of, and cache over here is you want to put in dcache. Dcache is the data cache. So basically you put in dcache with address and number of bytes. So let's say you know that the beginning matrix is at the variable x and 1000 elements. Each element is an integer, which means it's 4 bytes. So in that case, you would start from address would be x, the address at the starting address. Bytes is 1000 multiplied by 4 because there's 1000 elements. Each element is 4 bytes. And then the last argument would be dcache. All right, so that's how you can do the cache flush. Oh, also don't forget to add this. Include system cache controller. All right, so that's the first task. Get rid of things in the cache. This is where I would load the metrics. You might have noticed that size X, size Y, size Z, that's the size of your metrics, which you can reconfigure right here. Size X and Y over here is 22,000. It's kind of like the two number that I put in to make sure it's actually not way too big. Otherwise, you spend forever trying to run this. It's not too small. You can change it to make it smaller. And one thing I assume is X and Y are the same number. So you're dealing with a square matrix, not some rectangle and odd shape size matrix to make life easier, right? Over here, we load the file. You can kind of improve this by loading this in parallel as well. You use what you learned from project 1 to spawn another thread to load the file. That works too. This is nothing. Basically, we go and free all the metrics we allocate so far. Don't have to edit anything here. Your code, this is kind of like the second task. Make sure you implement the correct version of matrix multiply without the fancy tricks you apply. This is like a classic matrix multiply. It should be really easy. So there's a question on the chat, like to make the load faster, we can perform 2 loads into different threads. Yes, that can improve the load time a bit. But once you do that, you might have then realized that, hey, the bottleneck becomes the IO. Sometimes the IO doesn't really handle, doesn't scale really well. So it kind of depends. So that's one thing I want you to play around with. Because if you try to load in parallel, I will give you credit for that anyway, for the optional task, right? So if you read the assignments, there's like the last optional task. There are multiple of them that can be possible. I want you to throw around different ideas that you learn from this entire class, from project 1, project 2, and project 3, and see what can you do to squeeze out the performance. And the more tricks you try, so this is more effort based than performance based. So I want to see what else you try. What have you tried? What works? What doesn't work? Right? Uh, so multiply base is the simplest version of matrix multiply. Go do it directly as if it's the normal definition we learned in our math class. Compare results. Doing is basically doing nothing except compare your output with the reference solution. And my bad, this should be, I think, yeah, this should be reference.in. So make sure you fix that. We are reading reference.in to compare the results, right? So that's one thing that I noticed that might be wrong. Sorry. Basically, you want to make sure we have this and we test the solution. Okay. Oh, it's already correct. So no worry. You don't need to fix anything. So F test is the reference. It's already open up the correct one. F out is your own output from the program. So basically what it does is compare the two solutions, your solution and the reference solution. It has to match. Right results basically over here. Make sure your result from the matrix multiply is written to F out in the same format as the reference solution. Exactly, yeah. So you can use buffer as well. Yay. So that's another thing you can do to make things faster. And it's actually pretty handy tricks when you have to deal with I/O, actually. Yeah. Buffering and threading can make things faster. Load metrics. This is again simple. Open up the two input metrics and load them. You can load them in parallel. You can load them normally. Multiply is where the chunk of the implementation goes. This is when you optimize the metrics multiply. So your code goes there. The rest are basically over here. What we do is open up multiple files: the input, the output, the reference. And then we would clock, right? We will do the baseline implementation, and then we do the multiply for the baseline. We will compare how long it takes with your own implementation. Yes. So the question is multiply based, basically metrics multiply without optimization. Exactly. That should be like at most like 1 hour of implementation with all the debugging to get it right. You can basically take one row, multiply with one column, add them together. That's it for one entry, and do it for all the row and columns, like a normal matrix multiply. All right. Any other questions? So the task 3 is basically asking you to do a block matrix multiply. Block matrix multiply would do the matrix multiply in a way that we do one small chunk at a time. That small chunk should be made to fit, right? Basically to fit within the L1 cache. That way, when you are multiplying this thing inside the block matrix multiply, you don't have thrashing. Basically, it would try to make sure everything fit within the L1. And then if you look at how it reads the element from row to column, the second matrix you're multiplying with, it's not really cache friendly because it goes column, 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 column. It's never in the same block, right? So can you do row multiply by row by doing something with the second matrix? Things like that can actually improve the performance quite a lot, right? You can also do a parallel version of block matrix multiply where you would multiply multiple blocks in parallel. As long as that fit within L1, it can make things faster as well because you're doing multiple multiply and add at the same time, right? You basically try to do parallel programming on this. So that can also make things faster. All right. Any question before we adjourn? When it retrieved to put into the cache, how much? So the way the caching work is your data access by default put that data in the cache, put that address in the cache. So it bring in the entire cache block, right? So let's say your integer is 4 bytes. Let's say integer is 4 bytes. In the Intel CPU, the cache block is 64 bytes cache block, right? So when you load the entire cache block, you are loading 16 different integer around that one integer address into the cache. So it brings in the entire cache block at a time from that one data access. Yeah, it should be patched. It should be patched. Oh, download it now. It should be the correct one. Sorry. All right. Any other questions? And if you have anything with the starter code, let me know for sure.
Ajahn ครับ
ครับ
in the starter code, right, when we compile it, it's not working on Mac OS because in the C flag it's
Oh, you use the server. Use the server. Don't do it in Mac OS because Mac OS use CLang, which can be annoying to deal with if you compare that with like standard C. So it's much simpler to stick with the server like Linux based, Unix based OS. Otherwise, some of the flags is different. Basically, it's like something that would have the same flag, but in CLang, it might have a different flags.
so in the starter code it's M32,
Yeah.
but I change it to pedantic and then everything else works. So is
Oh,
that
so if you
okay?
yeah, if you know what flag to change and you basically change M32 to pedantic, it works too.
Okay, so I can just submit with that, right? Pedantic.
Sure. Because in this lab, we'll do a demo. So we'll talk about that in the next lecture. We'll have a demo slot that everyone sign up for because I want to learn like what are different things you do because that's the fun part. Uh, so instead of having the typical like assignment, I would have a subset of you in a group coming and demo your code so that you can take a look at I so that I can take a look at what you do and at the same time. Um, Hopefully also preventing people copying each other's solution and at the same time also having your friends look at like what you implemented versus what they implemented because that's kind of like it's knowledge sharing, which is awesome. uh you can do it in Putty. That helps quite a lot. Like use Putty to SSH to the server. Much I think it's much simpler. How to That's a great question on the chat. How to measure the time when you do parallel programming in without including the time to create the thread. Don't worry about the time to create the thread. Actually, I want I rather see how much performance gain can you get when you spawn more and more threads. When you look at parallel programming, the way you analyze the time, you want to kind of dig deeper, let me know so I can add that toward maybe the last lecture before we adjourn for this semester. There's quite a few things that you want to consider.
the time to spawn and create a thread matters. But in most cases, the cost get amortized over the complexity and how much time you spend on the main function of the program. So if there's a benefit in running the bulk, like the main task of the program, most of the time it's kind of like much more beneficial to do the parallel programming.